realistic. Bist du der Chairman? Gut. Kann ich akzeptieren. Nachdem ich den Chairman nicht gleich zu Beginn zitiere, kann ich nichts falsch machen. Problem.
Geometric numerical computation, and today Mr. Lubich presents us long time step methods for oscillatory Hamiltonian.
Well, this is a talk on numerical methods for oscillatory problems, and I should say that it is based essentially on two sources. The one is the second edition of our book with Ernst and Gerhard Wanner, in particular chapters 13 on the constant frequency case and 14 on the varying frequency case. And the presentation essentially follows a review article that we wrote last year with David Cohen, Tobias Janke, and Katina Lorenz. Well, what the aim is should become clear, or should be illustrated by this picture. Suppose we have some differential equation which has an oscillatory solution as indicated here. And if you want to get an accurate approximation to such a solution with a standard numerical method, what you have to do is to take small time steps which follow these oscillations in many small steps. And what you see, just by following me, this takes a long time. What we would like to do instead is to have a method which allows to get the same accuracy with much larger step sizes going over one or several quasi-periods. So in most cases, most examples that I present later, epsilon will represent something like the wavelength of the oscillation, and we're interested in integrating at least over time intervals of length 1 or even larger. So having such large time steps, that is the goal, and having accuracy with it, that's the other goal. Now, what I will tell you is, first of all, about some problem classes of Hamiltonian systems where different types of numerical methods are needed. And this essentially depends on whether frequencies and the corresponding eigenspaces are constant, or whether they vary in time or even depend on the solution. And then I will talk about some construction principles for such long time step methods. And if one looks at the literature, there are not so many building blocks. So I will talk about these. And then there are essentially two different classes of methods, the one for constant frequencies, the other one for varying frequencies. If I would have 2 more hours time than I have here, I will tell you about these trigonometric integrators, about the long-time properties, energy conservation, and the like. I don't have these extra 2 hours, fortunately for you. But I would like to mention that in the workshop next week, David Cohen and Ernst Heirer and myself will talk on this kind of problems, this kind of methods and on their properties. And in this talk, I will then concentrate on methods which are applicable when the frequencies are varying, and this leads to the class of so-called adiabatic integrators. So let me come first to some problem classes and illustrate it by mechanical examples, which again depend on whether the high frequencies that appear in the system are constant or whether they vary. Well, we'll be concerned with Hamiltonian systems. So if we have a Hamiltonian function h depending on momenta and positions, these are, of course, the canonical Hamiltonian equations which we want to solve. And on the following transparencies, I will give you some examples or types, some classes of Hamiltonians which lead to oscillatory behavior, and which we would like to treat in a numerically effective way. So let's first turn to systems which have oscillations at high frequencies, but where these frequencies are essentially constant. And this comes about if I take an equation like this one, which essentially corresponds to a system composed of harmonic oscillator, and add some moderate potential to it. And now the high oscillations appear if A, the stiffness matrix here, is a matrix of large norm. So this is always to be assumed to be a matrix which is symmetric and positive semi-definite. In this case, a constant matrix. M is always a positive definite mass matrix. You won't miss much in the talk if you always think of M being the identity matrix. And U is a smooth potential with moderately bounded derivatives. Now, a nice mechanical example, which is just of this form, is given by such a Fermi-Pastor-Ulam chain, where you have mass points connected by springs, and say by two different types of springs, by stiff harmonic springs with a stiffness constant, with a spring constant 1 over epsilon square, where epsilon is small, and another type of soft nonlinear springs which would correspond to this potential U up there. Now, and if you choose coordinates such that you represent the positions of the system by, on the one hand, by the elongation of the stiff springs, and on the other hand, by the midpoints of the stiff springs, then you will end up with a system of exactly this type, where this matrix given here is simply a matrix as indicated here. It has the 1 over epsilon square. There's one part corresponding to the slow variables, which would correspond to the midpoints of the stiff springs. And the 1 over epsilon square would multiply the fast variables, which would correspond to the elongations of these stiff springs. Now here we have of the high frequencies that appear are just small perturbations of the frequencies which correspond to the linear system here. And well, here of course we have constant matrices M and A, and this leads to high frequencies which are not exactly constant, because in the linearization along a solution of course, the U gives a contribution, but this is a small contribution corresponding to the high frequencies, which are of size 1 over epsilon in this case. I would, however, like to advert you that you can have constant high frequencies even in systems which do not have such constant mass or stiffness matrices, as indicated here, but which are, for example, of this form, where you have a mass matrix which depends on the positions, where you have the stiff oscillatory part, which corresponds, so the fast components, which in this talk we always carry the subscript 1, whereas the slow components will carry the subscript 0. This has constant matrices, but there is, again, another matrix here which combines all of them, but I assume that this term is small, vanishes as Q1 vanishes. Now we are interested in solutions which have bounded energy, then Q1 would be of size epsilon in the elongation, and so the R would be closed there, and we would have some perturbations. Now this looks somewhat artificial, but it is this class of problems which appears in a number of applications. For example, if you consider a triatomic molecule like the water molecule, where you have stiff springs modeling the elongations between the molecules, but also the angle. If you put that into coordinates, you will end up with something like that. And David Cohen has recently developed methods which apply just to this case. But what one uses here, essentially, both for the analysis and even for the construction of the method, is that the frequencies remain essentially constant. Now, the situation is different from, well, it's substantially different from a numerical viewpoint if the frequencies depend on time or depend on the solution. Let's first consider the time-dependent case, where the simplest example would be a harmonic oscillator where the frequencies depend on time. So we have then a motion with a quasi-period approximately epsilon, but the frequencies would change on a slower time scale of 1. So here we have here these two time scales, the slow time scale of the change of the frequencies and the fast time scales of the oscillations. And methods which work well for the constant frequency case typically don't work at all, or don't work in a reasonable way for cases like this. An important property of these systems is that the action, which is the energy divided by the frequencies, this is a so-called adiabatic invariant, which says that this action remains constant up to perturbations of size epsilon over very long time intervals in negative powers of epsilon. Now, here we just have one frequency. Of course, we can have several frequencies. Then we would have a system like that and add a potential. Again, we would get adiabatic invariants associated with each of the high frequencies appearing in such a system, as long as these frequencies remain separated. So, but now, of course, these frequencies depend on time, and they might cross or come close together. And in that case, when the eigenvalues, when the frequencies almost cross, then these actions are no longer preserved approximately, but they are fast transitions from one level to another level, which also create additional problems to the numerics, because these transitions have to be followed. Well, actually, a particular case of the previous one is adiabatic quantum dynamics, where we have a Schrödinger equation with a Hamiltonian operator h, which depends slowly on time t. Well, for sake of simplicity, let's take a finite state Schrödinger equation where h of t is just a Hermitian matrix. And then this is again a Hamiltonian system if, in the canonical setting, if you separate real and imaginary parts of psi and the corresponding energy function would just be the inner product of psi with ht psi. And in this case, the adiabatic invariants corresponding to each of the eigenvalues of h of t are just given by the components of C in the jth eigenspace. And they remain almost constant, again, as long as the eigenvalues remain separated, and then other effects appear. So finally, let's come to the case where the frequencies depend on the solution itself, depend on state, depend on the positions. So this would be a situation where I have a Hamiltonian with a constraining potential, V of q, with a large factor of 1 over epsilon square in front of it, where this V of q has the property that it takes its minimum, say 0, along a manifold, and transversal to this manifold grows quadratically. And in that case, if I choose appropriate coordinates, this V of q would be just of this form, again with fast oscillatory variables q1 and rather slower variables q0. And this A1 would be symmetric positive definite. So an example of this kind would be such a multiple spring pendulum, as indicated here, where the frequencies of the oscillations now depend on the angles. And this looks like a very simple problem, but if you try any of your favorite methods on it, I'm sure you'll run into problems rather soon. So if you have stiff springs connecting these, do not impose that the angles are almost fixed, as we had it in this triatomic molecule before. But just put stiff springs in between. This puts really a challenge to numerical integrators. So the goal in each of these cases is to have numerical methods which go in long time steps over the oscillations. So now let me come to the second part of my talk, where I will tell you about some principles on how to build such long time step methods. And essentially, well, I would know of 4 such building blocks, which I would denote as averaging, splitting, linearizing, and co-rotating, and which I would like to explain you in the next few minutes. So actually it's, well, not even a handful of them. But there's one additional one which appears to be very worthwhile to keep in attention, namely, it's certainly a good idea to preserve the symmetry of the method. So the method should be time reversible. This really pays off. And of course, we are dealing with Hamiltonian system, so the natural question after all these activities in geometric integration, what about using symplecticity here? Well, from a practical viewpoint, one can say, well, to enforce symplecticity is often too much to ask for. It may become extremely difficult to construct methods which are symplectic. That's the one argument. The other argument is it is not clear what, in the case of these long time steps, the effect of symplecticity is on the behavior of the method. This we had yesterday in Ernst's talk, where we saw that the nice explanation of the good favorable properties of symplectic methods, all the theory refers to the case where the time step is small compared to the wavelength. And this is just the situation that you don't want to have here. Here we want to have the product of time step with frequency large, and then the backward error analysis does not, as we know, it doesn't directly apply. And it's then not quite clear what is the role of symplecticity in such methods. So now let me come to the first construction principle. And this says it's not a good idea if you have an oscillatory solution that you just make isolated evaluations of the function along this oscillatory behavior, because essentially you make a random choice. So instead of taking isolated evaluations of oscillatory functions, aim at working with average quantities. Seems well, that's easy to formulate. It's not quite so clear how to put this into practice. And let me give you one example how this can be done. Let's take a second order differential equation of standard form, where the right-hand side can be split into slow forces and fast forces, where the name suggests that F slow is changing more slowly than F fast. And now a standard method for second order differential equations would be the Sturmer-Vallee method, written down here, which of course just makes a pointwise evaluation of F. On the other hand, if we look at the corresponding formula for the exact solution, written down here, then just for the remainder term of Taylor's formula, we see that instead of a pointwise evaluation, we should have here an average of F along the solution on this interval from, well, between t minus h and t plus h. Now, let's take this as starting point for the construction of a method. So here the formula is once again. And we had the splitting of F into a slow part and a fast part. And now an interesting case in many applications is where the fast part is relatively cheap to evaluate, perhaps concerns only a small part of the whole system, whereas the bulk of the computations would go into an evaluation of the slow part. So we would be interested in evaluating the slow part only at rather large time intervals, well, as I showed it to you on the first transparencies, going over several of these frequencies. Now, since it is choosing slowly, we just freeze the slow part over a time step and approximate the integrand here by the slow part evaluated at the current approximation point Qn, plus, and well, here we leave the fast part variable, where u should be now an approximation to q. And the approximation that we choose here is just to take the second order differential equation, where we use exactly this right-hand side given here. So instead of the f of u, we make the splitting where we freeze the slow part. But now, if we put this approximation into here, then of course we just have the same formula as previously, but now for the u. So this whole integral that we get here is nothing else than u of h minus 2 times u of 0 plus u of minus h. So that's the same formula as above, but now applied to this differential equation. Now this now leads us to a numerical method where we solve this differential equation, which doesn't use evaluations of the slow part, only evaluations of the supposedly cheaper fast part. And of course, I cannot solve this exactly, but I solve this with n micro steps over the interval from minus h to h. And I use the formula that I had obtained previously. So I take, to advance my numerical solution to get the qn plus 1 from the old values qn and qn minus 1, I use this difference quotient. And on the right-hand side, I just take the numerical solution obtained from solving this equation. And you can do the same game by using a corresponding averaging formula for the velocities, and take something like that. Well, as it stands here, it doesn't look like an averaging method, but from the way it was derived, it was clear that the idea was just to approximate this integral. Now, in the literature, we find several different ways of approximating integrals of this type. I should mention the reversible averaging method by Ben Leimkuhler and Sebastian Reich. People from numerical homogenization, Bain and E, and Björn Enquist and his collaborator Tsai, also developed methods along that line, which they call the heterogeneous multiscale method, and which just corresponds to the case where one replaces the whole interval from -1 to 1 over a shorter interval and replaces this averaging kernel by an appropriate renormalized kernel on this shorter time interval. So the methods they propose would be somehow in between the method that's standing here and the Sturmer-Vallée method, where one has just a point evaluation. So this working with averages is certainly one good idea. Another idea that is very helpful in many cases is splitting. So let's illustrate this for the Hamiltonian, which is built up of a kinetic part, a potential which is responsible for fast motion, and a potential for slow motion. And we take a splitting in the way indicated here, that we put together the kinetic part and the fast potential part, and we approximate the flow of this Hamiltonian system over time step h by taking first a half a time step just with the slow potential, then a full time step with the kinetic plus fast potential, and again a half time step with the slow potential. And this leads to the so-called impulse method, which in the first step just modifies the momenta. Then in the second step solves the Hamiltonian equations of motion corresponding to this system, which would be just q double dot equals minus the gradient of the fast potential over a time step. Of course, in general, I cannot do this exactly, so I would do this with micro steps over the interval, and then again I use a correction of the momentum using the slow potential. So this method first came up in molecular dynamics in the early 90s in these papers, and there's an interesting modification to this method by Bosco Garcia-Chia, Justin Cerner, and Bob Skeel, where they avoid evaluating the slow potential at this oscillatory quantity, at the oscillatory solution, but rather replace the slow potential by the slow potential at an average position, where this average position would again be computed using an auxiliary fast oscillating differential equation somehow related to that one. So this is the splitting idea, well, in that case combined with the averaging idea. Another idea that's often quite fruitful is just try to isolate a dominating linear part and then use the variation of constants formula. So if I have a differential equation of that type, where A is positive semi-definite, well, write it as the square of this matrix, the square of a matrix omega, then write down the variation of constants formula as given here with this cosine and sine matrix and this integral. Now use this formula just over one time step and replace this integral by a quadrature formula, and then you will get something which falls into the class of so-called trigonometric integrators. Well, the name just comes from the cosines and sines appearing here. For example, you could take the simplest Phelon method, approximate g by a constant function over the interval, and then you will end up with a method which has been proposed by Gauci in 1961. Or just take the trapezoidal rule for approximating this integral, then you will end up with a method which has been proposed by Teufelhardt in 1979 and which can be viewed as the impulse method that I proposed to you previously applied to this particular system. So this class of methods is actually quite old, but it was only in the last years that their properties became understood. So far we have 3 building blocks: averaging, splitting, linearizing. Now let's come to my last building block, where we do not work with the original coordinates in which the system is given, but try to choose co-rotating coordinates which adapt better to the oscillatory behavior of the system. And let me illustrate this for the case of this Schrödinger equation with a time-dependent Hermitian matrix, h of t, and a small parameter epsilon. So in this case, well, if I divide by epsilon, the psi dot would have the 1 over epsilon in front. So we would have here an unbounded, well, we would have a matrix whose norm goes to infinity as epsilon goes to 0. And it's clear if we use a standard numerical method on that, we'll encounter difficulties. So the idea is to take a transformation from the original variables psi to new variables which are denoted by eta by some suitably chosen transformation matrix T, which may be time dependent. And well, if I insert this into the equation, then I just get the differential equation for eta with a matrix S, which takes this form. And now the goal would be that eta should be smoother than the original psi. And this will be the case if the matrix which I get here is bounded uniformly in epsilon. So that would be the aim, to find a matrix S epsilon of t which is much smaller than the original matrix which has this 1 over epsilon in front. Well, there's a simple first idea. Just freeze the slowly varying matrix h of t at the midpoint of the interval and transform in such a way that if h were constant, we would transform back always to the initial, we would transform the solution back to the initial value. Now this would be just given by the exponential of this h star given here. But if we look here, then since the variation of h over the interval of length, since the variation of capital H over the interval of length small h is of size small h, and this is divided by epsilon, we do not get a bounded matrix in this way, but one which is h over epsilon. And though this is a large gain by a factor of h compared to in size to the original matrix, we haven't got something which is uniform in epsilon. And the effect of this is that in general, the step sizes are still restricted by something which is of the order of the epsilon. Still, this can be a very reasonable approach, especially if h of t, if the derivatives of t, if the derivatives of this matrix are small, say if h is a constant matrix plus something which carries a factor epsilon. Now this transformation goes back to Lawson in 1967, so it's quite old. And it has been exploited for some problems in quantum mechanics and other areas. Well, Ari Isel has done work of that, and Degani and Schiff did nice work on that too. But somehow this is not yet satisfactory. Instead of the h over epsilon, we would have to something which we like to have something which is bounded uniformly in epsilon. And this we can get by, well, either by rediscovering or afterwards finding in the literature an old transformation from 1928, goes back to Born and Fock, which goes as follows. We diagonalize our matrix. So with a diagonal matrix lambda, unitary matrices U and U star. And we look at the components of psi in the corresponding eigenspaces. So these would be the coefficients in this eigenvector representation. And then I multiply with the phases, which are just defined as the integrals over the eigenvalues given here. And now the effect of this transformation is shown in this picture, where I take a solution component in the original variables, which would be highly oscillatory, as given here. And the effect of this transformation is the line that you see here, which from behind certainly looks almost constant. Well, if you take a magnifying glass, it's not really constant. It has small oscillations still. But of course, this is a much smoother function and therefore numerically more agreeable function to work with than the original oscillatory function to approximate. So if we do this transformation, what are the differential equations then that we get for this? These adiabatic invariables eta. Well, I should go explain where does the name adiabatic come from. Well, Born and Fock used this transformation in proving their version of the quantum adiabatic theorem, which just states that eta, or the absolute values of eta squared, which are the actions of the system, they remain almost constant as long as the eigenvalues do not cross, and that's just what you observe here in a particular case. So now in these adiabatic variables, we get the following ODE. If we take this Q-symmetric matrix W, which is formed of the time derivative of this unitary matrix U of t times U, then we get a differential equation which has a nice form. Well, it's a sandwich form in which W of t is sandwiched by these rapidly oscillatory diagonal matrices, phase matrices given here. And now, of course, it's clear that the norm of this matrix is bounded independently of epsilon. So epsilon does no longer appear in the matrix here. So we have a matrix here which is bounded uniformly in epsilon. So we have achieved our goal of a transformation which removes this factor 1 over epsilon here. And therefore, the derivatives of eta are bounded by the norm of W of t. Now we can think of approximating the problem in these adiabatic variables eta. And we just note what are fast and slowly varying quantities in this equation. Now we see eta dot is bounded, so eta is changing slowly. W of t doesn't contain the epsilon, so we consider this as a slow quantity. And then there are, of course, these rapidly rotating phases given to the left and the right. So a simple method is obtained by just freezing eta and W over a time step to make a linear approximation to the phases, phi of t, over a time step. Then we obtain, well, using the variation of constant formula, something like that, we can then integrate exactly over the time step, and we get an integrator in these adiabatic variables, which takes the following form. Well, the method I've written down looks almost like the midpoint rule applied to the system. So if you omit the sinc function, then it will be just the standard midpoint rule corresponding to the system given here. And now this sinc function corresponds to the integration done here. So we take the average, not the point evaluation, and this leads to this mollifying sinc function given here. Now this is just a very simple and certainly not the best method to recommend. There are much more accurate methods available, but somehow based on this same principle that you separate the time scales between the fast rotating matrices to the left and the right and the slower variables W and eta. And Tobias Janke has done very nice work on that. However, I want to warn you that you may run into problems just in the situation when eigenvalues come cross. Because the whole idea of this method here was to separate timescales. But when eigenvalues come close to each other, then W becomes a large matrix and its derivatives become even larger. So this is a fast changing matrix in that case. And on the other hand, when eigenvalues come close, then these differences become small. So it's no longer true that this is fast rotating. And the whole idea between the separation is not really satisfied here. So what one has to do in practice then is to have a suitable adaptive step size selection which goes near these crossing zones or near avoided crossing zones of eigenvalue with small step sizes and takes large step sizes outside. So this is an example of a method where we choose different coordinates which rotate according to the motion in our system. So we had now these 4 building blocks of averaging, splitting, linearizing, and co-rotating. Now, the different classes of methods for constant frequencies, where essentially we can work with the original coordinates, and we have in particular these trigonometric integrators. And, well, as I mentioned, I will not tell you about these in this talk, but see next week. And now let me come to further problems with varying frequencies, where this idea that I showed you previously for this time-dependent Schrödinger equation is now carried over to classical mechanical systems. So let's consider a mechanical system with time-dependent frequencies. So given here, well, the m of t is not the critical thing, but we have the 1 over epsilon square multiplying here, and we have a time-dependent matrix A of t. You might add a potential u of q and t, which is all of whose derivatives are bounded uniformly in epsilon. This doesn't cause many problems, so I will stick to this problem in the following. And if you apply any of these methods, which work so well on problems with constant frequencies, like these trigonometric integrators, they fail miserably on these systems. So what we do is something of the spirit that we had in the previous example. We change coordinates in a way that we can separate the fast and the slow timescales in our systems, which are completely mixed up in this formulation. And we can do this by time-dependent canonical linear coordinate transformations. And the nice thing about it is that this can be done numerically by standard numerical linear algebra routines. So essentially what I need is a Cholesky decomposition of the matrix M of t and an eigenvalue decomposition of the stiffness matrix. Now if I carry this program through, I will end up something which is very close to the adiabatic variables that we had previously in this Schrödinger example. And on these, I use one of these adiabatic integrators, which we also had previously. Now, this program has been carried out in chapter 14 of our book. And there's nice work on methods of this type in the thesis of Katina Lorenz from last year in Tübingen. So, how does this work? So, what we do is to make a series of canonical linear coordinate transformations, which I will not detail you because this would become messy formulas and become somewhat boring, but I would like to indicate the basic steps. So first of all, we do a Cholesky decomposition of the mass matrix and then transform variables so that we have a system of the same form, but now replace the mass matrix by the identity matrix. Then on the resulting system, we of course have a transformed stiffness matrix, and this is now diagonalized in this way, where we have on the one hand a block of psi 0, which then corresponds to the slow motion of the system, and a block which carries the frequencies omega j. So recall the a is still multiplied by 1 over epsilon square in the equations. So these will become these divided by epsilon become the high frequencies of the system. And now we have this splitting corresponding to the 0 block here and to this diagonal block here. And we split the positions into Q0 corresponding to the first part, and Q1 corresponding to the second part, and the corresponding splitting for the momenta, which somehow corresponds to slow and fast variables. It's then useful to rescale positions and momenta so that they become of the same size under the assumption that our system has an energy which is bounded uniformly in epsilon, and this requires rescaling here by epsilon to minus 1/2 for the positions and epsilon 1/2 for the momenta, which unfortunately leads to a term which has a negative power of epsilon to minus 1/2 in front of one of these terms which result from the transformations that we have done previously. So that's the bad news, but the good news is that I can get rid of this term again by another canonically transform. And at the end, I'll get a system which looks like that. So here's just a kinetic part for the slow variables. There is a kinetic part for the fast variables. And this quadratic potential part with the same matrix, again, for the fast variables. And then we have some coupling terms, L between the Q and the P's, and the potential part with the symmetric matrix S of t appearing here. Now, if you write down the equation of motion, well, you have some linear functions in P and Q, F0 and G0 here. And for the fast variables, you get the system with this Q-symmetric matrix given here, which carries the 1/epsilon and the frequencies, and some other terms which do not do much harm, in particular which carry no 1/epsilon. So the dominating part now is given by a time-dependent skew-symmetric matrix of size 1/epsilon. Well, and that's just the situation we have encountered previously. If you recall this Schrödinger example, there we had a skew-Hermitian matrix divided by epsilon, 1/epsilon. And so what we do is we diagonalize and then integrate, transform to adiabatic variables, and then integrate this. So, I needn't look at all these formulas. We diagonalize the matrix which appears here. Well, this can here be done by this constant matrix gamma. We introduce the phases as the integrals of the eigenvalues given here, and transform to these adiabatic variables which correspond to this transformation given by the matrix here, has here the rapidly rotating phases, and well, it's useful again to rescale with epsilon to minus 1/2. With this rescaling, I obtain that for systems with bounded energy, with energy bounded uniformly in epsilon, the eta would be of magnitude 1. So now I write down the equations of motion in these variables. And what I get is that now the slow and fast degrees of freedom are only weakly coupled between the P0 and Q0. These are the slow variables. The eta are the fast variables, but there's a factor epsilon appearing here. And for the fast variables, for the eta, I get exactly the matrix of the time that I had previous. Recall this sandwich construction of the W framed by these oscillatory phase exponentials. And there's some extra term here, which is also highly oscillatory. So this P1 and Q1 are highly oscillatory matrices, which contain also the phases here. Now, there's one important difference to the example that we had previously. In the Schrödinger case, this matrix W was Q-Hermitian. This is no longer the case here. It's, however, a matrix which has zeros on the diagonal. So if you multiply this out, it still has zeros on the diagonal. And this is important for ensuring that the etas are, again, adiabatic invariants. And actually, as it turns out, you consider the components of this variable eta and take their absolute value squared. Then you obtain functions which are adiabatic invariants. and which can be just interpreted in the original, or well, maybe not quite the original, but in coordinates a few transformation steps earlier, just as the actions, namely the potential energy of these oscillatory parts divided by the frequencies. So you still have this classical interpretation of the adiabatic invariance as the actions in this framework. Now let me come to a numerical integrator. So we work with these variables P0, Q0, which are the slow variables, and these adiabatic variables eta. And what we do is now a mixture of all that we have had previously. We use an adiabatic integrator for the adiabatic variables. We use a splitting scheme, and we use some averages for the highly oscillatory integrals that appear for the highly oscillatory terms that appear in the system. So for the slow variables, we just use, in the first step of the splitting method, a symplectic Euler method. As you recall, we had the system given here, which behaves nicely in epsilon. So I'm aiming now at the method which, for the case of epsilon tending to 0, turns to the Sturmer-Vallee methods for the variables P0 and Q0. And this I obtain by first taking a symplectic Euler step. And now for the oscillatory parts, which fortunately still are multiplied with an epsilon, I don't take point evaluations, but take averages with a linear phase approximation and then an analytic integration of these integrals. Then I propagate the adiabatic variable eta with a full time step of an adiabatic integrator of the type that I described to you previously in the case of the time-dependent Schrödinger equation. And then I do a third step over half a time step, now with the adjoint symplectic Euler method in the slow variables, and again with a suitable average of the Q1. What one gets in this way is a symmetric scheme, which for epsilon going to 0 turns to the Sturmer-Vallee method in the slow variables P0 and Q0, and which has nice approximation properties. So it can be shown that uniformly in epsilon for step sizes which can be as large as the square root of epsilon. And this limitation by square root of epsilon essentially comes from the linear phase approximation. So if you make something better here, you can go to even larger time steps. And then you get second order accuracy in the positions and first order accuracy in the momentum. And the constants that are here, that's important to note, they do not depend, they're independent both of epsilon, and they also do not depend on higher derivatives of the solution, because the solution, of course, is highly oscillatory, and one wouldn't like to have solution derivatives in these estimates. So the constants here just depend on derivatives of the slowly varying functions that we had previously. Now let me turn to a numerical example. Let's take a mass matrix, well, just the identity. Let's take a stiffness matrix of the type given here, well, and a small epsilon 0.01. And there's an extra parameter delta in this matrix, which has the effect that as delta becomes small, eigenvalues approach each other at t equals 0. So if delta is 0, we have a crossing of, you see, for t equals 0 and delta equals 0, we have the double eigenvalue 3. So for as delta becomes small, there's an almost crossing of eigenvalues given here. And what I show in the lower line, in the lower row of pictures, is the norm of the time derivative of the orthogonal transformation matrix, which takes this matrix to diagonal form. And you see that the peak at 0 evolves just at the position where the eigenvalues come close. Now the effect of this on our adiabatic variables eta is the following. So we here have a two-dimensional system, so we have two of these adiabatic variables indicated here. And now as delta becomes smaller, they do not remain nearly constant. Well, here's a hump appearing. And as delta becomes smaller, essentially there's an exchange of between the values that they have here. For very small values of delta, there's just an exchange between the values of eta and here it's a sudden transition zone which has to be treated carefully in the numerics. So in this area, you cannot go over with the large time steps that our method allows us to take away. Here we can take very large time steps, but we must capture this zone. And let me just show you. The step size is chosen by a symmetric adaptive step size selection strategy applied to different variants of delta. So the thicker the line, the smaller delta is. And this shows that for small delta, I have to choose small step sizes here and get up again. And the accuracy obtained with all these values of delta and all these step size sequences is about the same in all the cases. But you run into big troubles when you just take fixed step size in this area. Now this was the time-dependent case. Finally, let me say a few words, not much, on the case when the oscillations are not explicitly time-dependent, but depend on the solution itself, are state-dependent. And we may take a system like this and possibly add a smooth potential. And now what can be done is that the methods and techniques that we had in the time-dependent case, they can be extended to this situation. So now we take a set of nonlinear coordinate transforms to more convenient variables, which still can be done numerically, or at least approximate versions of them can be done numerically. And in this way, we also obtain long time step integrators for systems like that. But I must say, as long as the eigenvalues, as the frequencies remain well separated. Of course, we must expect the same difficulties that we had in the time-dependent case, but the difficulties are even worse, because in the state-dependent case, for state-dependent frequencies, in the limit as epsilon going to 0, the slow motion of the variables q0 and p0 is no longer a fixed limit if eigenvalues are very close to each other. And this was first worked out in work by Tarkans in the early 70s. So any numerical method must have difficulties in this case, but away from these crossing zones, we can take large time steps even in such cases. And the methods, I must warn you, have become quite complicated, and they have been worked out in the thesis of Catine-Lawrence. Well, that ends my survey of long time step methods. Thank you for your attention.
Thank you.
What happens to the sum of these adiabatic invariants or these action variables in the last case? I mean, can you say anything? I mean, there's this exchange, right?
No, there's no conservation of the sums or nothing. There's nothing like that.
Right.
Even in the time-dependent example that I showed you in one of the pictures, if you take the sum, it wouldn't be conserved.
So there's even an arbitrary exchange of energy and the fast.
Well, in time-dependent case, this can be described by this Landau-Zehner formula, of which Stefan Teufel is the great expert to any order in epsilon. I mean, of course, on the analytical side, you can do expansion which go much further, which are much more accurate, but they depend high derivatives of all the appearing solutions, and this is not something that one would like to do numerically.
Could you just clarify the following? My understanding was that you are choosing your adiabatic variable as a smoother function compared
right? Yeah.
However, in those figures that you showed for time-dependent case,
Yeah.
you clearly see that this is fairly steep transition. And
Right. But this steep transition is just at one point where the eigenvalues come cross. And so you need a step size selection strategy which captures this behavior and takes small step sizes in this area and large step sizes outside.
right.
Whereas with a standard integrator, you would have to take small time steps just all over the interval.
Okay, but just to clarify your message, I mean, say for example, I have a problem and I would like sort of to apply the technique that
Right.
you are proposing here. I don't know a priori whether my eigenvalues are well separated or not.
Yeah.
And so basically, you know, I don't know whether they are.
Yeah, with this strategy, you needn't know a priori. You have to compute them anyway. I mean, the method, of course, has extra cost compared to other methods. You need to compute the eigenvalues in every time step.
Okay.
You need to compute the transformation, and from essentially what is monitored in the step selection strategy is the change of the transformation matrix. I mean, if you observe something like that, then you might get the idea maybe it's the right time to choose a smaller step size. So roughly, this is what's behind.
But you in your Hamiltonian, you include both sort of kinetic and potential energy. Can you comment on some constraints that you may need for potential energy? Because you do have coupling through the sort of potential energy as well. You separate into fast and slow variables,
Right.
basically your kinetic part.
Yeah.
Do you need any special restrictions on the potential part, or you don't?
No, well, on the potential part, of course, well, in this time-dependent case, let me see where I have it. In time-dependent case, I assume that I have this quadratic part. I might add another potential, which does not depend on epsilon, which may just be any smooth potential.
Okay, so yeah, thanks.
But the dominating part, determining the high frequencies, should come from these two terms.
Reina?
Yeah, at the very start of your talk, you said it was generally a good idea to use self-adjoint methods.
Right.
So can you comment, or do you have any idea why that is?
Well, what would be the alternative? If you think in very traditional methods, explicit Euler method would create energy, implicit Euler method would dissipate energy, and none of that is good in these problems. You don't want to excite the oscillations, you don't want to damp the oscillations.
All right, so should I think, say, for instance, that you like your, say, if eigenvalues are on the unit circle, you like them to stay there? Is that sort of
Well, that's certainly the philosophy behind that, yeah.
There's also work actually by Ernst that showed that some symmetric methods don't quite conserve energy so well, and Eberhard, I think, right? I mean, you have examples where that argument seems to break down, right?
No, well, I would a consider it as a necessary, not only in some cases not sufficient condition for good energy conservation. I mean, you wouldn't expect good energy conservation over long times with a non-symmetric method. Yeah, but so you should go for at least for a symmetric method. Maybe it still doesn't work, but that's the least you should look at. And so, I mean, all the methods that have been constructed in this era, they for oscillatory systems, they are symmetric. A few of them are symplectic, but the symplectic ones are not necessarily better than the non-symplectic ones.
I must say, this is something I'm not 100% clear about, because you could have a method that preserves the energy exactly, and that was not self-adjoint.
Well, but preserving the energy is still something different from. I mean, if you just take a standard explicit Euler method, we could project down onto the energy. So the energy is kept, but numerically experiments show that this is not a good strategy. You get all kinds of artifacts. Just keeping the energy exact is far too weak a restriction. So in this way, symmetry is much stronger and gives more in quality.
I suppose Molly would get these transitions correct as well, right? I mean, in your last part, I mean, these transitions between adiabatic variables. I mean, because it's essentially
No, well,
all that with
what it
time,
does,
right?
no, as long as the eigenvalues stay separated, the modified impulse method indeed can be shown to yield the expected order that one knows from the constant frequency case. But the analysis is not trivial. The analysis uses exactly the transforms that we have here. So you reinterpret the modified impulse method in these new variables, and then you can show that. But it's not at all clear what happens to the modified impulse method in this when eigenvalues almost cross.
Well, that's chaotic anyway, right? It's hard to predict.
No, but I mean, you might like to follow these transitions in the adiabatic variable, and with a small step size, you can follow it. But
Well,
the
it's
modified impulse method will just not notice that this happens because it doesn't monitor them.
You mean it could overlook them essentially? I mean, it could even see.
You do not control the quantities which determine the behavior of these transitions. You don't have the eigenvalues. You don't have the transformation
in
matrices.
Molly, you basically you're using a small time step for that part of the dynamics anyway.
Yeah, but it's not. You don't have the separation. You just.
So you would need a small time step.
I mean,
long time step also.
be careful.
Yeah, I mean that's not immediately clear.
Don't know where it is.
I mean, of course, if you have an additional potential here, you could take Molly by splitting between the slow part and then keeping just this part, and then taking small time steps on this part. Well, if you want to, if this can be done, okay. But the goal here was just to take large parts, large time steps, even on that. And this doesn't cost so much as long as you can afford numerical linear algebra in doing a Cholesky decomposition and an eigenvalue decomposition. Then you can take these large time steps even here. You cannot apply Molly with large time steps in any way here, because here you don't have any splitting. Of course, if you have the extra potential, then you can do that. But even in our algorithm, which includes the potential, you would split here.
So let me thank once more for this nice talk.